All right. Thanks very much. All right, this is distributed pure functions. I'm Richard Feldman. So at a previous job, I worked at a company where we had a gigantic fire hose of data. And it was petabytes and petabytes just coming in. And one of the problems that the company had was, hey, we're pretty sure that there's like valuable stuff we could get out of this, but how? Anyone ever had a problem like that? You work at a company that's got gigantic amounts of data, yeah. And then there's this question of how do you turn that into something valuable and useful? So the way that we came up with to do this at this particular company was we had all these functions running on this data across a very large distributed system. And some of the functions would say, okay, here's this, we ran this function on this data, we're going to produce this output, and that's going to go off and get displayed for someone somewhere. This one's going to go do something for someone else, and actually this one's going to feed back in and produce more data that's going to churn through this whole process, and around it goes. Now, it was a very important property of these functions that they were pure functions. And the reason for that, by the way, if you're not familiar with what a pure function is a function that has no side effects, so that means that it's not allowed to modify outside state, so it's not allowed to like modify global variables or do I/O or things like that. And then also, if you give that function the same arguments, it has to give you the same answer every time, no matter what. If you satisfy both of those constraints, then you're a pure function. And the reason that we needed these all to be pure functions was because we had a different group of people building the distributed system from the people who were actually writing these functions that were operating on the data. So the people who were writing the functions were domain experts, but not necessarily expert programmers. They had some really relevant domain expertise that could use these functions to generate value for the business, but they had pretty minor background in programming. They kind of like knew enough to be able to write the functions, but they didn't necessarily know how to write them in a way that was pure. The concept of like, well, don't use side effects. Make sure that if you get the same give the same arguments, you get the same answer. They were, let's say, inconsistent about being able to do this. So it would have actually been quite useful if, back when I had worked at that company, if I'd had access to the Rock programming language, which is the language I've been working on for the past several years. You can learn more about it at rocklang.org, and the tagline is that it is a fast, friendly, functional language. Now, so in Rock, every single function is pure. Like if you call a function in Rock, it's always going to have those properties, doesn't do side effects, and if you give it the same arguments, it's going to give you back the same return value, guaranteed. So on the home page, you can see this little code snippet here. This is just an example of Rock syntax. So it's saying credits equals, and then list.map, passing in two arguments. The first argument is songs, and the second argument is this function that says, give me one argument named song, and then it's going to return this string performed by, and then a little string interpolation here, song.artist. So this right here is the function name. So this is the function that we're calling. We're calling list.map. How many people here are familiar with map functions? Okay, pretty much everybody, so I'm not going to get into too much detail on what that does. Songs just being the list of songs. We'll talk about what that list data structure is a little bit later. And then here's the actual function that's going to operate on each one of those songs, and then that return value is going to become each element in the output list. Okay. Now again, because Rock is a purely functional language, this function is guaranteed to be pure. No matter what, there's just no way you can implement this function in a way that's not pure, simply because Rock doesn't have primitives for making impure functions. There's no way to run a side effect in Rock. There just isn't even syntax for it. There's also no way to like directly mutate something, which could cause a side effect, or directly read from like global state, which could cause a side effect, or an impure function. So guaranteed, no side effects, and same arguments to this function means same return value. Now, this is something that's quite useful if you're going from one core to multiple cores, so like parallelizing things. We'll talk more about that a little bit later. And it's also useful if you're going from one machine to multiple machines, so distributing the workload across a distributed system. I'm going to talk more about both of these later, but one of the things I want to talk about first is where this sort of has limitations. There's a lot of hand-waving that comes up when it comes to pure functions and parallelism and distributed systems, where there's this idea that's like, hey, as long as your functions are pure, everything's going to be easy. And it's like, what do you mean everything? Because it turns out not everything's easy. Some things are easier, yes, there are some very useful properties here, but also there are some things that just are not magically fixed. You actually still have to think about them, and maybe the way that you think about them is a little bit different than if you don't have a pure function. But in this talk, I want to tease apart exactly what does that mean? Like, what are the actual benefits that we're getting if we are doing parallel as well as distributed pure functions, and what are the things that pure functions don't fix? So, just to talk about the sort of sequential version of this, let's say we have list.map and we've got a little list of songs over here, so we've got 4 songs in it, let's say. Ordinarily, in a sequential version of list.map that's not distributed and not parallel at all, it's going to run on one CPU, represented by this little icon here, and it's going to take that function that we wrote that takes a song and then returns whatever it's going to return, and it's going to run that on song 1, and then we're going to have this output list, and it's going to put that in the first element of that output list. And then we're going to do the same thing for song 2, and the same thing for song 3, and the same thing for song 4, and this is just the CPU marching through them, doing them one at a time. Now, because we know that that function that's going to run on each of these elements is a pure function, no side effects, same arguments, means same return value, we know that it's safe to parallelize this. So we can, if we want, take that function and let's say we have 4 cores in our machine, just run it 4 times, once on each of those cores, and then use that to just generate all 4 of those answers in parallel, such that we don't have to wait for it to just do them sequentially. We can, all else being equal, just sort of theoretically do them all at once. Now, this might lead you to the conclusion, and this is definitely something that I've heard people sort of hand wave away in the functional programming world, of just like, hey, so just always parallelize. Like, look, this is better. Like, doing things like 4 of them at once is better than doing them one at a time. Obviously, it's going to be 4 times faster, right? That's just math. Kind of. Maybe. Yeah. Always parallelize, what could go wrong? Well, let's talk about that, because this is the first of several things that I'm going to throw a little bit of cold water on. There's this awesome paper that, shout out to Jonathan Megan, who introduced me to this paper. It's called Scalability, but at what cost? And when they say cost, there's an acronym that they're inventing here. Configuration that outperforms a single thread. So what they did in this paper is essentially they went back and looked at a bunch of, I think it was mostly like graph algorithms. They looked at a bunch of other papers and talked about, oh, look how amazingly well we parallelize this thing, and it's just so fast. Like, look, number of cores, like line goes up, this is so great. They said, okay, but what if we took this problem as you described it and then just wrote the fastest single-threaded implementation we could come up with? How does that compare to your incredibly, line goes up parallel version? And spoiler alert, in an overwhelming number of cases, they found that there is no configuration of the parallel version that outperforms the best single-threaded version. In other words, like if you're constrained to be like, this is running on one machine, it's like no matter how well you parallelize this thing, no matter how much work you're doing in parallel, the overhead of that parallelization, of like distributing it across multiple cores and the memory locality issues that come with that and all the other stuff and like gathering the results up, the overhead of that always exceeds what you would get by just doing it sequentially in one thread, to the point where even like if you just, in theory, if you had an infinitely large machine, okay, maybe at some point you could win out, but not in the course of like an actual real machine and not in the course of like that actual problem. So this is a really important thing to keep in mind. It's like just because we are able to, theoretically, parallelize or distribute these things doesn't mean that's automatically faster. In fact, quite often the reverse might be true. So this is another special case of always measure. But at the end of the day, when we're talking about these general properties here, what we're talking about is like what's possible, not necessarily what's automatically fastest. That's a really important distinction to make. Okay, so what could go wrong by just always making this parallelize? Like something that people have brought up to me is like in Rock, hey, why don't we just have this list.map function? Why don't we just make part of the implementation of map that it'll just automatically parallelize these things for you? Because, hey, we can, right? These are all pure functions. We know that it's safe to do that. It's never going to cause any correctness problems. It's never going to cause any data races. Yeah, that's true, but it might also slow them down. So there is a cost to doing this. It's not necessarily free to do that from a performance perspective, even if from a theoretical perspective it is safe to do that. So this coordination overhead, this like gathering overhead, granted gathering things up, that's more of like a map reduce thing, which we'll talk briefly about later, but that doesn't really come up in this particular case, but there's definitely overhead to doing these things. So to me, a better design is to just have explicitly 2 different functions. Like you have a map and you have a map parallel, and then that way the user can opt into one or the other, depending on whether they think that the parallelization cost is actually going to be outweighed by the complexity of like how much work is being done in these individual functions and so on and so forth. Like they can actually measure, try it both ways. And one of the advantages of having pure functions everywhere is that switching between the two to try it out can be as simple as just like map versus map parallel. You just be like, yeah, I already wrote all my logic in a way that's amenable to parallelization, and that has the benefit of now I can just switch back and forth, no problem, and very quickly answer the question, is it actually going to be faster to parallelize? So to me, that's an example of a concrete benefit to doing things in a purely functional style, not, oh, we'll just automatically do it and everything will automatically get faster. So we have the map parallel version of things that runs on 4 cores and the map version that just runs on 1 core sequentially. Now, I bring this up because, well, one of the reasons I bring this up is because I have seen quite a lot of examples in the functional programming community of people talking about this sort of general idea of like, it's the end of Moore's law, individual CPUs are not getting faster, like clock cycles, clock speeds are not increasing the way that they used to. The future is parallel. Like if we want to run fast systems in the future, we gotta be able to take advantage of these cores. And one of the things that people will sort of conclude about this is like, this is why functional programming is awesome. It's going to save us from the end of Moore's law. These are slides from a very famous functional programmer named John Hughes. So I'm not picking on him. Okay, I am picking on him. But it's okay because he's famous. So, so these are some slides. And no, really the reason I'm picking this is just that like, I wanted to have something concrete to talk about because I hear this a lot from a lot of different voices, and I think it's important to draw this distinction here. So this slide says, data is immutable, it can be shared without problems. That's true. If you do have all pure functions, all of your data is semantically immutable, you don't have data races anymore. That's cool. I mean, you know, for this crowd, I don't want to get into the whole like Zig versus Rust thing, but you know, when people do talk about like what's the big benefit of Rust, they talk about like, well, you don't have to worry about data races. But the old school don't have to worry about data races is just don't have shared mutation at all. If you don't have any mutation, they don't have data races, so cool. Now there's obviously trade-offs there. It's not like that's a free lunch either. But it does mean that like, yes, you can share data between threads if it's semantically immutable without worrying about data races because that requires mutation. No side effects means that parallel computations can't interfere with each other. Again, that's true. Like we saw in the list.map example, totally beneficial. Now the problem that I have with this slide is the last bullet point, which is just evaluate everything in parallel. And as I previously noticed, yeah, what could go wrong? Just evaluate everything in parallel. Everything's just gonna be faster. It's like, not necessarily. To me, it's like more like, well, why functional programming? It's because you can evaluate everything in parallel and you can very quickly evaluate whether or not running things in parallel is actually going to be faster because your code's already written in a way that's amenable to that. This is another example from that same talk, and I think this actually really drives home really well why just having pure functions and then running them in parallel or in a distributed system is not automatically going to be faster. One of the things that's going on here is that it's not just about, okay, yes, semantically things are immutable, but also what are the specific data structures and algorithms that we're using in order to make them be pure? So in plenty of cases, like this quicksort example on this slide, this is not really the same thing as the normal sort of traditional quicksort that you might see. Now, if you're not familiar with Haskell syntax, I want to just like point out a couple of things about this. But the idea that this is classic quicksort, I would never use the word classic to describe this quicksort algorithm. And we will go through it in a second and we'll see if you agree with me on that. It does say, hey, this is something that you can divide and conquer, which is fair. But let's just look at like what this is actually doing. Now, if you're familiar with traditional quicksort, this is a little animation of quicksort. We've got this array, and you sort of pick two pivot points, and there's this little swap. See, they swap. Okay, cool, they're swapping in place. This is really important. There are no new arrays being allocated. There are no new allocations of any kind. It's just swapping in place. There's going to be lots of great memory locality to all of this stuff. This makes a lot of sense. I can understand why you would use the word quick to describe this sorting algorithm. Okay, now let's look at the one on the slide. This right here is a linked list. This is another linked list. This is another linked list. This is plus plus, and these plus pluses each concatenate the linked lists together, which is a linear amount of marching through heap allocations and allocating a new linked list for each of those. So this is 5 linked lists and 5 plus heap allocations. It's actually way more than 5 plus heap allocations. That's in the absolute best case scenario where each of the lists has only one element in it, but it's actually linear in the number of elements, so it's worse than that. And this is 2 recursive calls here that are not tail recursive, and so this whole thing is not stack safe either. You could potentially blow the stack with this implementation. So comparing that to this, I would not quite describe this as classic quicksort. I think it has some relevantly different characteristics there. So again, this is a really good example of the types of things that they're talking about in this paper, like at what cost? It's like, can we think of a single-threaded implementation that might be faster than this parallelizable quicksort algorithm? Like, yeah, I'm pretty sure the classic like actual single array in place, no heap allocations involved whatsoever, is probably going to always outperform this thing. I have not run this test, but I would be really shocked if it did not turn out to be one of the things that they talk about in this paper, you know, across lots of different programming languages, where, yeah, no configuration of this, no matter how much you parallelize it across a single machine, is going to outperform the really obvious, like in-place, single-threaded version that doesn't do all these heap allocations. Now, like I said previously, Rock is a fast-friendly functional language, so I really care about this fast thing. Like, to me, I don't want to just hand wave away and say like, oh, it's all pure functions. So like, parallelization, like Moore's law, is fast, right? I actually care about the like fast in the sense of like, no, like your code actually executed faster in real life. So I gave a talk at Strange Loop a couple years ago called Outperforming Imperative with Pure Functional Languages, and I did talk about this quicksort example. On this slide in the talk, I had, this is basically the same algorithm that I saw there. Like I said, this thing floats around a lot. It's weird, it won't die. But somebody wrote a whole blog post called Efficient Quicksort in Haskell, where they said, okay, this looks really neat and it's cool that it's 3 lines of code and whatever, but it's not actually efficient. That's right. And then he wrote out what would an actually really doing the in-place like real quicksort look like in Haskell. And essentially it looks like this. It's a little bit longer. And it's using these functions unsafe read, unsafe swap, unsafe slice, which are basically just, actually forget the whole pure functional thing. We're just going to like mutate stuff in place because, yeah, that's like what quicksort needs. Now, granted, it is possible to have a language that is semantically all pure functions that can be competitive in quicksort. I'm totally spoiling the end of the talk here, which is like basically we were able to get it so that quicksorting 10 million unsorted numbers, we were faster than JavaScript. This is the cheating Haskell that was using all the unsafe, like non-functional stuff. Java and Go, only C++ was faster than our implementation. And this was all just doing pure functions and then just leaning on it really, really hard on our optimizer to turn it into essentially the like in-place version that's not doing any heap allocations and stuff like that. So as I talked about in that talk, the way that we were able to do this is, number one, we're using LLVM, which none of those others were. We're using unboxed values as much as possible, so minimizing heap allocations, like this was a 0 heap allocation operation by the end of all the optimizations. Static reference counting, so we do reference counting automatic reference counting for memory management, and the static ref counting that like sort of elides the reference counts at compile time based on realizing that they're going to sort of cancel out, turned out to be sort of key to getting that result there. Tail call optimization, really, really important if you want to have a fast functional language, because that basically means that all those recursive calls, if you're writing things in a way that is tail recursive, they just get optimized into a while loop, which is what you want for quicksort. And finally, and this is kind of the big one, opportunistic in-place mutation. So this is where basically we have this concept in Rock of if something is unique in terms of it doesn't have any active references to anything else, then when we have an operation that would ordinarily duplicate it and create a new one, at least that's what you would expect it to do, semantically looking at it, we can say, well, hang on a sec. Rather than creating this whole new value and then just like copying over all the values from the old one, why don't we just take the one we've already got that nobody else has any references to and just mutate it in place? And that's how we're able to optimize our way into having something that performs as well as sort of traditional imperative in-place mutation quicksort, because at runtime, it actually is doing the imperative in-place thing. The difference is that semantically, it's all pure functions, and it's just the optimizer doing that because it realizes that it's not going to be observable to do it in that way. Okay. So, taking this back to our list.map example and applying this to the parallel world, and in the future we're going to talk about it in the distributed world, this data structure, this list in Rock, is not a linked list. This is, I guess the general term for this is something like a growable array. So this is like in C++, this would be called vector. In Rust, this would be called vec. In Zig, this would be called array list. But as I previously mentioned, we do automatic reference counting. So in addition to the sort of growable array semantics that you find in those, there's also a reference count associated with it. There's also a little bit more. We also do this thing called seamless slices kind of behind the scenes for a little bit more sharing between these things. But at the end of the day, like fundamentally, the relevant part is that it's one contiguous allocation in memory, like an array. And then if you need to grow past that, you allocate a new contiguous thing and then copy all the elements over. So what this means is that if we are reference counted with opportunistic mutation, is that if we are doing this list.map operation on all this, and whether this is concurrent or if it's single-threaded, if we know at runtime, we say, look, there's no other references to this list. Like we can see the reference count is 1, so nobody else is looking at this thing. It's not going to be observable if we just mutate this thing in place, even though semantically it will still feel like everything is immutable. Now, this does depend on what is the actual output value of each of these functions. So for example, if this input value, let's say that this thing is like, I don't know, 24 bytes in memory. So each of these elements is 24 bytes. If this thing is returning something that's like 64 bytes, well, okay, maybe we can't do this in place after, as we might be able to if it's exactly the same size. So if the output of each of these is going to be the same size as the input elements, well, guess what? we can just write the answer in place. We don't need to create that whole brand new list and then deallocate the old one. Instead, we can just write them in place. And this also works with the parallel version. Like there's absolutely no possibility of any kind of data race. We don't need any locks. There's no possibility of contention. We can just completely, at compile time, say it is completely 100% totally safe to just run each of these functions on a different core and then write the answer directly back into whatever the input slot was. And there's no iterator invalidation. There's all of these things that we don't have to worry about because we know that these are pure functions. There's no chance that any of these functions is going to be able to read from any of these others, because if they were trying to do that, that would increase the reference count of the list, and so then they wouldn't be eligible for this optimization. And also there's no chance that any of them is going to be able to modify any of these others, because whether or not that would change the reference count, you just can't do that in a purely functional language. It's like not expressible to say, I want to reach out and mutate some other part of the list. So this is a cool and like genuinely useful benefit of doing this, is that we don't have any overhead of contention or locking or anything like that. From a safety perspective, instead the safety just comes from the semantics of the language being like these are guaranteed to be pure functions, and that combined with opportunistic mutation means that we can actually do something that you absolutely can do in any imperative language, but with a lot more sort of be really careful, don't do this, don't do that, don't do the other thing. You have to have a sort of certain set of rules if you want to get this same level of performance from using an imperative language to express this directly, rather than having the optimizer do it like we do in Rock. Okay, so from a perspective of like, this scalability but at what cost, like asking the question, could you do better with a single-threaded implementation? Still the case is, the answer is potentially yes. Like there is still that overhead. Even when we've sort of minimized this as much as possible, it is entirely possible that for a given set of inputs and a given set of functions like this, you might find that the single-threaded version is faster. But the good news is that we have really, I think, minimized that overhead as much as possible. Like the cost of switching to the parallel version in this world is as low as I can really imagine it. Even if I were writing in an imperative language and saying, I don't care about safety guarantees or anything, I'm just going to try and do this as fast as possible, I don't really know how fundamentally you could get it significantly faster than what we got here with these optimizations. So that to me is a good example of saying we're taking these sort of guarantees of pure functions and using them to milk as much performance as we possibly can out of something that fundamentally, again, I'm just changing list.map to list.map parallel, and hopefully it'll result in a speed up. Okay, now a really important question here is, okay, we're able to do this in parallel across however many cores you've got, but how many cores are actually available? Like, the number of cores that you can parallelize over is a really big important factor in terms of how much of a speed up you're possibly going to be able to get from this. Well, in this example I said let's assume we have like 4 cores, but there might be way more songs in this. Like maybe there's not 4 songs, there's 4,000 songs, 4 million songs, 4 billion songs. There could be quite a lot of those, and maybe there's more than 4 cores, but there's a pretty big discrepancy in terms of how many cores are available depending on what type of hardware situation you're talking about. So shout out to the Futhark programming language. This is a high performance, purely functional, data parallel array programming language. If anyone had asked me earlier on when we were doing the little languages game before the talk started, that would have been a fun one for someone to bring up. I could be like, I got a slide on that. So this is a kind of a research language. I don't know of anyone using it in production, but basically this is a language that is designed to let you write purely functional code that runs on the GPU. And there's a lot of cores on GPUs, let me tell you. But this is also another good example of, again, looking at what is the actual cost of that. Because when you go from a CPU and multiple CPU cores to the GPU, there's this new source of overhead, which is that the GPU and CPU have different memory. So even though you have a much higher number of cores that you can parallelize your operations over, you now have this new cost of literally getting the information from CPU land memory over to GPU land memory. And famously, when you're doing GPU programming, this can be one of the highest costs that you have to deal with, is just getting the memory from point A to point B. So again, it's not just about how many cores can you throw at it, but also what are the other sources of overhead that are going on there, and how much do those affect and like overcompensate for, or sorry, overcome or not the amount of savings that you're getting from being able to parallelize it across more cores. And this of course leads us to the next thing, which is like, well, let's say I've got one machine and even distributing it over all of those GPUs is not enough. Now I actually need to do more computation than is possible across one machine. Now I need to switch to multiple machines. Shout out to another programming language, Unison. So this is a language that is designed to make it easier to run pure functions across multiple machines. So actually taking it from one machine to a distributed system, and again, using some of these nice properties of pure functions to make it so that you can do certain things in the background. Now this is where things are going to get a little bit more interesting, because now we're moving from the one core to multiple cores land to one machine to multiple machines. And just like in the case of moving from one core to multiple cores, it's not as cut and dry as just like, oh, you have pure functions, everything is automatically better and is just going to run faster. In much the same way, we're going to see the same kind of thing, but in different dimensions when we go from one machine to multiple machines. So we talked previously about this idea of parallelizing across multiple cores. Now let's say that I wanted to switch from list.map parallel to list.map distributed. Doesn't that sound nice? You just say like, hey, I would like a distributed system. Yes, please. And you just press a button, and now it's just automatically distributed. Okay, there's a lot of like infrastructure stuff here that would have to go on. You have to get your code deployed on all these things. There's a lot of stuff that I'm hand-waving away here, but let's stipulate that you've got the code deployed, it's the correct version of all the code, you've got all the machines set up, they're all connected, they all know about each other, you're doing all the infrastructure stuff. I'm a languages guy, I like to just leave that to people who get paid more than I do. But let's pretend that you've already got the distributed system itself set up. What are the characteristics that we can get out of pure functions that will help us do this correctly and be able to not worry about certain things that we might otherwise have to worry about if we weren't dealing with pure functions? Okay, so first thing is that obviously, you know, I've got 4 machines pictured here, but we're not going to want to just run one individual function per machine. We can do better than that. So it's probably going to be more like we have one machine that's going to be assigned some certain number of songs or elements in the input list, and then each of their cores is going to be running multiple of these computations. But it's not that simple anymore. It's not just like, well, we have this input list, and it's like, here's our list, and then we just start running stuff on it. First, we have to actually get it to the machines. So if you thought going from the CPU to the GPU was a lot of overhead, let me tell you about the network. Because when you're talking about sending memory, like that is pieces of information from one part of an individual machine to another, we're really talking about like kind of nanoseconds levels of latency. Now we're talking about milliseconds. So talk about your like, hey, can we do better single threaded? It's like, yeah, by default, definitely. But this is not just about saying I've got this one big fixed chunk size of work that I want to do and I want to distribute it across more cores. It's also about like, what if the amount of data that I want to process just does not fit on one machine? Like at that previous job I was talking about, you got petabytes and petabytes of data. You can't just be like, oh, I'll just put it all on my laptop, you know, and I'll just churn through it and just do CPUs, single threaded. Like that's not going to work anymore. Like it just won't even fit. So there has to be some amount of either distributed or at least chunking at the very least to be able to just work through that entire workload. So now we do have a more serious latency consideration to deal with. So you know, milliseconds of network latency. We also have a serialization cost. So in order to get these things over the network, I can't just be like, here's a pointer, just dereference it, nothing bad will happen. It's like, no, that's not going to work. We got to actually serialize all the data and then send that over the network. And then once it gets to the other side, usually there's also probably going to be some sort of deserialization cost. Now, if you want to get super fancy and do things with like arenas and indices and stuff like that, you can work really hard and do like what Andrew has done in the Zig compiler to make it so that the deserialization cost can be as minimal as possible, and you don't have to like do a bunch of pointer rehydration and stuff like that. However, one way or another, there's going to be some serialization cost. There's going to be some cost to like getting that stuff across the network and then getting it back into memory on the other side in a form that's usable by the machine over there. Usually it's more like JSON, which is about as far as you can get from zero cost of serialization. But the point is that this is an additional cost that we're paying. When you're going from CPU to other CPU cores, you're not serializing that. You're not paying that cost. You're not paying for network latency. And you're also not dealing with faults. Like, okay, yes, hardware faults can happen, like cosmic rays, whatever. Okay, but generally speaking, when we are writing software and we're writing it to run on one machine, it tends not to burn us if we don't think about hardware faults that much. There's like enough redundancy in the system or things like that. If you've got a big enough system, okay, fair enough. Like you can have like hard drives fail and stuff like that. But not to the degree that we have to deal with in a distributed system. Now the level of faults is just on a totally different level than what you have to deal with one machine. So there's this entire new category of problems, or at least like a much bigger category of problems that can happen in addition to these other costs. So for example, let's say that we have a disconnection happen. So I'm like, hey, process these songs, this machine in our cluster. And it's like, sure, I acknowledge that I've received your message. I'm going to start processing these things. Like, cool, how's it going? And it's like, I'm dead. I'm like, oh, Okay, well, how far did you get? I'm still dead. I can't tell you how far I got. That's a problem because now we don't know how much work has been done. Another thing that can happen is arguably even worse, depending on your perspective, is I'm like, hey, here's this stuff, and it's like, cool. Hey, how's it going over there? It's like, still working on it. Okay. It's been a while. How's it going over there? Still working on it. Okay. Can you stop? Like what, at some point, we have to make a decision about like how long is too long. Do we want to like pull this off and like how far did you get before that happened? So a really nice property of pure functions is that they're safe to retry. So if I find out that this thing got disconnected, I don't have to worry like, hey, did you send a bunch of emails and like how many of them did you actually send? It's like, that's not a thing with pure functions. They're like designed to be like, yeah, you give it the same arguments and all it does is just return an answer. So yeah, I'm not gonna get my answer back, but I can just go ask any other node to run that pure function and it'll just give me back the answer. And if later on this thing gets reconnected and it's like, oh hey, I got the answer for you, I'm like, cool, I already got it from somebody else, so I don't care, that's fine. But it's harmless is the point. It's not like you're having some sort of duplicated effect. Similarly with the timeout case, it's like, yeah, you can just duplicate the work. It's like, this node's taking too long, I can just be like, hey, you look free over there. Can you do that same thing? I know it's going to be duplicated work, but again, that's potentially better than like waiting for this thing. It might take a year. I don't know. But I don't have to know. I don't have to worry about that because I can just duplicate the work. Or to give a more sort of concrete example, I can say like, look, I'm just going to put a timeout on this thing. If any of these nodes in the cluster is taking longer than what I've decided is an acceptable amount of time, I don't have to worry about like how far did they get. I can just be like, yeah, you're done. That took too long. I don't care about your answer anymore. Just I'm going to have some other machine on the cluster go and do that. I can just have it redo the work, and yeah, it's going to be duplicated effort. Yes, there's going to be a little bit more delay, but I'm not going to have any correctness problems around that. I'm not going to have like emails getting sent multiple times or anything like that. So in other words, sort of boiling all this down, this is similarly to how it was safe to parallelize these things. A nice thing about having the guarantee of knowing that these are all pure functions is that it's safe to attempt to distribute them. If anything fails, like we get a disconnect, the machine's down, whatever, we can just automatically retry it on the same machine or retry it on a different node, and that's totally fine. If anything is taking too long, we can either redo it on a different node in the cluster, or if all else fails, if every single node in the cluster is like failing or just taking forever, you just be like, you know what? All right. We're just going to undistribute. We're going to go back to just, here is my one machine, and I'm just going to churn through these things one at a time. And I can do that and not worry that there's going to be any correctness problems, like emails getting sent or anything like that. Now, granted, you're talking about petabytes of data, and the one machine that you've got that is the only one that's left and able to work, okay, maybe that's going to take forever. But the important thing is that there's this entire category of problems and failure modes that we don't have to worry about anymore because it's always safe to redo all this work. So again, bringing this back to like, is this going to be better than the single-threaded version? Potentially not. Like, especially if we're getting lots of failures and stuff like that, if we're just getting timeouts left and right and disconnections and all this stuff, every single time one of those faults happens, we're introducing more and more latency to the system, and we're going to be paying for that compared to if we didn't have a distributed system. But the point is that we can recover from all these things much better if we know that all of the work that we're doing is pure functions. So for distributing to be a win, there's an important question of like, how big would this list need to be? If it's 6 songs, I can tell you right now, unless you have some really, really complicated function that you're running on each one of these things, it's probably not going to be a win to distribute it. But again, if you have petabytes and petabytes of data, distributing might be the only option, and that's always going to be a win because otherwise you're just not going to be able to get through the whole thing. You can't even fit it on one machine. So yeah, serialization costs, latency costs, faults, yeah. If it's going to be too big for one machine, you don't really care about how much these costs are because that's sort of what we're priced into. That's the only way to get the work done. Okay, so I think putting all this together, like honestly, a question that I've been asked is like, what should be in the standard library when it comes to like parallelization and distributed systems and stuff like that? If we're just talking about an individual list, I think like having a map distributed just doesn't make sense. Like I don't think we should ever put that in the standard library because if you're working with a workload that's so big that you want to do it on a distributed system, you're not really talking about an individual list anymore. I think that even though the properties of pure functions can be quite useful in that context, it just doesn't make sense to me to say like, oh, let's just pretend that you have one list. At that point, we need to start talking about streams and other sort of abstractions for the work that we're going to be doing. Just trying to pretend that you have one, petabytes long list in memory when you don't, I think is just probably not the right direction to go, even though from a properties perspective, we theoretically could do something like that if we wanted to. I've been talking a lot about map here. I'm not going to get into like a lot of details about like map and reduce, but I do want to make one really critical distinction here, which is that yes, okay, when we're talking about map, if you have pure functions, you can do all sorts of nice stuff in terms of running them in parallel, running them across distributed systems. But reduce, it's not really sufficient to, in the same way, to say, hey, if you've got a pure function for your reduce function, guess what? Everything's great, it's all gravy, and you can just you can run that in parallel and stuff like that too. That's not really the case. In the case of reduce, the property that matters more is commutativity. So if your reduce function commutes, then okay, cool, and the order doesn't matter. We can like run those things as we get answers back from the different parts of the map. That's all well and good, but even if it's a pure function, knowing whether or not that function commutes is really the determining factor as to whether or not we're able to like do that sequentially or better than sequentially. So this is an example of how just because everything is pure doesn't mean that we're automatically able to distribute or parallelize to the maximum extent possible. There are still other properties, such as commutativity of a reduce function, that give you, that sort of unlock more things that just having pure functions doesn't get you. So this is another example of, to me, saying like, okay, it's not just as simple as if we have pure functions, everything's easy. There's other properties that matter too, some of which are not really enforceable at a language level. I mean, there's probably some language that can tell you at compile time whether or not your reduce function commutes, but that's really kind of a separate thing from whether or not the functions are pure like they are in Rock. Okay. So we sort of talked about this, like going back to this example that I had earlier of like the pure function that's all this like giant fire hose of data and running all these different pure functions on it and having the problems of like the domain experts don't necessarily write pure functions, but if they do, we're able to get all these really nice properties out of this. We've talked about a lot of different sort of like failure modes and downsides and all these things. And one thing that I didn't mention though is that like there's more properties than just this that are nice. So like it is nice to be able to safely retry these things. It is nice to be able to safely time out and then redo the work. Also memoization, like caching, is really nice if you know the property that if you give this function the same arguments, it's always going to give you the same return value and not do any effects along the way. That's really helpful. If you know that you can do that, then that means you can just cache it where the key is the inputs to the function and the cached value is the output of the function. You don't need to bother rerunning the function. That's great. All of these things are examples of properties that we did actually make use of at that company, which was why we had this team designing this distributed system that other people were writing the functions on. We were able to automate a whole bunch of these things because as long as people did follow the rules, unfortunately we didn't have a language that automatically enforced them, but as long as you did follow the rules, we were able to just make it so that the throughput of the system was as good as we could get it without having to worry about individual people messing things up too much. Okay, now, all this is all well and good, but of course, a thing that everybody always brings up is like, okay, yes, it's all well and good if it turns out that your problem domain doesn't involve any effects and you have like pure functions everywhere, but what if we actually do have effects? Like what if I do actually want to send an email? Like what then? Okay, let's talk about that. So a very brief version of this is, and this is actually what we did at that company, is let's imagine that one of the things that these functions can return is a description of like, hey, I want you to do some effect. Now it's not actually doing the effect. This is just data. It's coming back and saying, let's pretend, for example, that it's a record and it says, we have a field in this record that's called effect and it describes, here's the effect that I want you to do. And that says just like email, so I want you to send an email. And then there's some data in the record also that's like, you know, what's the body of the email, who's it going to, you know, BCC and all that stuff. So this right here, what I have in this box, this is still a pure function. I mean, it's completely safe to retry. It's like, hey, I call this function 1,000,000 times on a bunch of different machines. It's like, cool. They all just return a record saying, please go do this email. Just returning a record that says, please go do this email does not actually result in any emails getting sent. If this gets disconnected, if it's waiting forever, doesn't matter because all it's returning back to me is a description of something that I want done. It's not actually doing the thing. It's safe to redo. Again, it's safe to memoize. All of the properties of pure functions that we want are still in full effect here. The only problem is that it's not actually sending the email. So this is a really common strategy in purely functional languages, is this idea of separating the calculation of what you want done from what is actually doing the effect. So in a distributed systems context, what this would mean is, let's say that we have all these inputs, we want to distribute them, we run them all in parallel. All of them are, like, or quite a few of them are potentially returning these descriptions of what we want done. The actual act of doing the effect is going to be a very different part of that system. It's going to be, for example, it might just be one machine. There's like one machine that's responsible for doing all the email. And so when we get this thing back, these things are going to say, okay, let's send messages. Message passing is another big thing in like distributed systems in general, but also in pure functional programming. Just saying like, hey, just go pass this message along. Say, hey, somebody needs to go send the email. And is this starting to sound familiar? This is the type of strategy that we can use to make sure that, yeah, we don't need to worry about all of this distributed work resulting in emails getting sent and ending up in unsafe or uncertain states. Instead, all we're doing is just passing around data, some of which describes work that we want done, and then we can really tightly lock down the one system that is actually sending those emails. And like that could be done with a queue or any number of different like infrastructure strategies. But the important part, the critical thing, is that it's not that we're sending these network requests over that are resulting in these emails getting sent immediately, but rather that we're maintaining all of the properties that we've talked about all throughout this talk of all these pure functions by saying we're going to pass around descriptions of effects rather than doing the effects immediately, and then having a completely separate system with completely separate characteristics and a lot more that we have to worry about that's going to actually execute the effects. Now, this is something that works at the distributed systems level, but it's also something that works in purely functional languages at the like basic, I just want to run a program on my machine level. So for example, in Rock, let's say I wanted to write a function that's called email file. And it's like, give me a file name and give me a destination email address. And I'm going to read the contents of the file and just email it to that address. This is like not something that people do all the time, but it's a really simple example of the type of thing. Like a question I get asked all the time is like, you've got a purely functional language, all functions are pure, but what if I want to do something? It's like, okay, well, this is how. So here's what that function might look like in Rock. So I'd say string equals file.read UTF-8, file name, so in other words, like read the contents of the file into that string, and then email.send, we're going to pretend we have used some library that's taking care of email sending, and then here's to is the destination, and then the body of the email is that string. Now, in Rock, we have this exclamation point operator. And this is actually doing a lot of work here. This is a bit of syntax sugar. And essentially what's happening here behind the scenes is that this exclamation operator is designed to make it look like we're doing sort of sequential imperative code. You can kind of imagine it like it was like an await keyword in async await. So it's like await file.read UTF-8 or await email.send. But the relevant part here is that all that this function is actually doing is it's just building up a description of work that we want done. So what this would essentially desugar to behind the scenes is something like this. It's not exactly this, but for slides reasons, I'm just going to kind of hand wave it a little bit. But the point is that it's just data that it's returning. So this email file function, yes, it is taking a file name. Yes, it is taking a destination, but it is returning just a piece of data. It's going to be something like what we saw earlier, where it says like effect is file.read UTF-8, and then the other piece of information in this record is going to be a function to run after that thing runs. So after we did the read UTF-8 and we have this string contents of the file, we're going to run another function which is just going to return another description of an effect, this time email.send, with the data in there. Now, it is true that unlike in, let's say, an imperative language, like basically like JavaScript or any other language where if we ignore the async await part, if I were to call this email file function 100 times, it's going to send 100 emails. Like every single time I call this function, it's like, yeah, we're doing that right now. In Rock, if you call this function right here that I've written, like this actual Rock code, if I call this 100 times, it will send 0 emails. Because really, I'm not kidding when I say it really is just building up a description of work that is to be done at some point. Now, what ends up happening is that when you call a bunch of these functions, it's sort of chaining all these things together. You can already see a little bit of the chaining here where we're sort of nesting one description inside of another one. The entire Rock program ends up being basically a gigantic built-up description of all of these things that you want. And then what ends up happening is that your sort of main function, where in most imperative languages, main is like, yeah, we're going to start doing these things eagerly right away. Main in Rock is basically just like, hey, give me one of these descriptions, and at runtime, I'm going to actually do all these effects and like chain all these things together and do all them like that. Now, if you look at implementations of like async await in a lot of languages, this is actually what's happening behind the scenes anyway. Like in Rust, you'll actually see like there's a data structure that looks a lot like this that's being built up behind the scenes when you're doing async await. It's just that in a purely functional language, we sort of make that be how we do all effects. We don't have side effects in addition to this. It's kind of like async await is how we do every single bit of I/O, etc. And one of the cool things about this is, just like with async await, you can now have some nice concurrency that goes on. Even though this sort of reads like sort of straight line imperative code, it can be scheduled differently. This doesn't have to be blocking other, even on the same thread. If you have access to one thread, like you're on a really limited virtual machine or something like that only has access to one virtual CPU, it can still do other work in other parts of the system while it's waiting for this async IO to come back. But in addition to that, this can be distributed across systems. Like if you wanted to, you could take this description right here and run these things on different machines, and it would work exactly the same way. Because essentially what we've got here is we've got these pure functions that are sort of stitched together. It's like a description of an effect that we want to do, followed by some sort of function to another pure function to run after we get the results of that previous effect. And I'm not going to get into it, but you can also do the same thing. Like you can incorporate concurrency into this and say like do these 3 things in a row and like do them all in parallel, or run them on multiple different machines. The really nice thing about this is that this sort of message passing, like describe what you want done rather than actually doing it, and sort of intentionally decoupling, here is the logic that determines what effects we want to run from here is the thing that's actually running the effects, means that if you want, you actually can distribute this code and have it run across whatever machines that you want. Now, as we've talked about, should you do that automatically? Very different set of questions and considerations there. But the point is that this is one of the cool things to me about purely functional programming. If I look at this code, I'm like, I don't know, this looks like normal I/O code to me. But what's actually happening behind the scenes is something that's subtly a lot more potentially powerful and a lot more flexible, because what it's actually represented as in memory is this separated out description of what I want done from the pure functions that connect it. Okay, so yeah, so pure functions that describe effects, or sort of conceptually async await, but either locally on one machine, which is pretty much how everybody does it. But if you wanted to, you actually could compile this down to something that would distribute it across multiple machines. Okay, so that's the answer to the question, like, what if we want to do effects? It's like, this is how we would do effects in this context, is by describing the effects and then separating out who actually runs the effects, which is going to be in a much more controlled environment. Now, the next question might be, okay, what if I don't want to do effects like that? What if I want to do actual side effects? Well, now you lose all the benefits, is the short answer. It's like, yeah, now it's not safe to retry anymore. Like if you have running this thing doesn't return a description of like, hey, I want this email done, it actually sends the email, you can't safely retry that anymore. Now you're potentially going to get duplicate emails if that thing gets disconnected partway through having done its job, and it come back and says, hey, I'm disconnected, and you're like, how many emails did you send? It's like, I don't know, I'm dead. It's just not safe to retry that anymore if it's returning not just a description, but it actually was doing the work eagerly as a side effect. It's for the same reasons it's no longer safe to do a timeout and then redo. You might be redoing some of those effects that you don't want to be redoing, and it's certainly not safe to memoize. In some cases it might be, but it's no longer sort of automatically safe. Like you don't know if the function is doing side effects, whether or not it's okay to skip doing those side effects when you're coming back and getting the cached version. So in short, there's a really, really important distinction between effects. I like to call them managed effects, where you're sort of describing the effect and then having a separate system actually run those effects, versus like running the function itself immediately runs the side effect. That's a really critical distinction. And as soon as you're in the side effects world, you lose all of those benefits that we've been talking about. So yeah, it's just going to make distributing harder if you want to be able to do side effects in your distributed functions. Okay, so to summarize everything we talked about. If you take nothing else away from this talk, I think the awareness of like this paper and sort of considering like, are we actually improving things by parallelizing them or by distributing them is a really, really important question. Sometimes the answer is obvious, where you're like, this data set is so gigantic it can't possibly be done on one machine. Fair enough, but I still way too often, especially in the functional programming community, see this sort of hand waving around like, yeah, you just parallelize it and it gets faster. Not necessarily. We talked about some sort of specific examples of that, and about how, although if you are in a language where every function is pure, you can absolutely swap between map and map parallel without even thinking about it. Just being like, yeah, just add those extra letters in there and let's just see if it's faster. I think that's a really important technique to be aware of, is that if you are writing your program in this style or using a language that automatically enforces it, it is really nice to be able to try those out and just see where the wins are, where things actually in practice are going to be improved or not by making things parallel. And I wouldn't agree with the like, just evaluate everything in parallel, obviously. we talked about how pure functions, although they do have a lot of concrete benefits that we talked about, they're not everything. It's not like everything just becomes trivial. MapReduce being a good example of this. Like really what matters there is it does reduce commute, not just as a pure function. There's more considerations than even just the overhead in terms of like the properties of your functions that determine like what you sort of can and cannot safely automatically optimize. But at the end of the day, I think there is just a lot to be said for having pure functions as sort of the foundation of what you're building. You do get all these really nice properties in terms of retrying things, timeouts, memoization, and I mean the list goes on. So at the end of the day, hopefully you now have a much better understanding of what are the benefits and what are not the benefits of distributed pure functions. Thanks very much.